Good evening to all the participants to the third day of this FDP, ATAL FDP on quantum computing and quantum machine learning solutions for sustainable solutions. Let me introduce our chief guest speaker for today, Assistant Professor Dr. Ankur Raina. Sir is working in the Department of EECS at IISER Bhopal. Before joining IISER Bhopal, Sir had worked as a researcher scientist at the Department of Electrical and Computer Engineering, University of Arizona, and with Professor Bane Vasek. Sir's research interests include classical and quantum information theory and coding, quantum optics, quantum cryptography, quantum algorithms, fault-tolerant quantum computation. Sir has obtained PhD from PMSL Group of the Department of Electronic Systems Engineering at the Indian Institute of Science, Bangalore, under the supervision of Professor Shyam Srinivasa Garani. Sir, we are very happy and it's a pleasure to have you with us amongst today to talk on the topic of basic quantum algorithms. Over to you, sir.
Okay, thank you so much, Dr. Deepa, for this kind invitation and such a warm introduction. So I would like to begin. I hope the introductory part was covered in the first 2 days. So I will go over the quantum algorithms, which is basically an application of how quantum computing works. And what we can do is I will go over the slides, the presentation, and if you have questions, you feel free to pause and we can do it in an interactive way. Right? And I have time until 7:30. Is that correct?
Yes, sir.
Okay, so shall we begin? Yeah.
Yes,
So
once
today,
can you just change the slide just to check if it is working. Yes, sir, you can please start.
yeah. So today, this is the outline of the talk. I will be covering these well-known algorithms, Deutsch-Jozsa, Bernstein-Raziran, Simon's algorithm, Grover's algorithm. And what we can do is, if you have questions, you can ask, and we'll see if we can cover most of it. And I will give you the main intent, the intuition behind these algorithms, how they work, and what kind of terminologies we are supposed to know as we go over these algorithms. Right? Uh, so this for this talk, I will need some preliminaries. So the preliminaries begin with the idea of Oracle. Oracle is a well-known concept in computer science, but from quantum computing point of view, and for the purpose of this talk, we will be treating the Oracle as this box, which takes n-bit strings to n-bit strings, and need not be equal to m, but typically in various scenarios they will be equal, and depending on the application or the problem statement, one has to design a certain kind of oracle. Right? So one can think of this oracle as a function which takes n-bit strings to n-bit strings. So, for example, if I were to make it very simple, if the input x is of n bits and f of x is, for example, 1 bit out, 1 bit output. So it takes n bits as input and it gives out 1 bit output. For example, it could be finding out the parity of the input. So does it have even parity or odd parity? So if the input x has even parity, or f of x will be 0, and if it has odd parity, if x has odd parity, then f of x will be 1. Now, in the context of quantum computing, what happens is we are required to do reversible uh, computing. So, in other words, given the output, one should be able to figure out the input. So, this goes in the spirit of reversible computing or reversible computation in quantum computing, because the circuits or the evolutions that happen on quantum states in a quantum computing setup are typically unitary. So any unitary matrix represents the evolution, and the idea of reversibility is to ensure that from the output that you are able to get back to input state. So this is the main idea of reversibility in quantum. Now, if one has to execute some circuits, for example, which have classical logic on a quantum setup, we will have to map the data into quantum states and hope that one can construct unitaries from which one can evolve the states and get back the input state from the output. So this is the main idea. And typically you have the input X, and then there are some supporting bits, namely the ancilla bits, and then there is some other set of bits, namely Y. And overall, if one has to make this computation from X to f of X reversible, this is typically the scenario. One equates the number of inputs to the number of outputs and ensures one-to-one mapping via this transform. So you have some input X, and there are some 0 bits, some bits that are initialized to 0, and then there are some more bits, namely call it Y. They can be 0, they can be something else. And the output is Y XOR X, and then you have some X and 0. So what happens from this setup is, given the output, one can figure out the input. So this is the main idea of reversibility. So having seen the output, one can figure out the input. Okay, now how does one map this whole thing into quantum setup? All you need to do is change the Boolean strings to quantum states and keep the strings inside the text. With this short small change, what happens is the bits are now elevated to quantum states, and one can look at quantum states and evolution of quantum states through the unitary, which performs the action of the function. So you have get X, and then we have some states that are initialized to 0, and then you have some get Y, some ancilla bits, and then the output is Y XOR X, X and 0. So with this mapping from the Boolean logic to the quantum setup, we are preserving the reversibility, the idea of reversibility, and at the same time we are able to execute this function via the unitary. Okay, so now this oracle has to act on vectors, right, or the states. So now if you have an n qubit vector, what we can write or think of is like an n-bit register. You have what is can be thought of as a quantum register, where you have n qubits, and each of them are zeros or ones in the computational basis to to get a feel for what is happening. So the bit strings x0 through xn minus 1, which is, for example, in a classical register, zeros and ones, can be elevated to a quantum state via the same notation, where the zeros and ones are now put inside the kets. So now, if I were to represent the state of a quantum state of a quantum register, I will consider ket x, and ket x can be thought of as consisting of a tensor product of single qubit states, where each of them can be 0 or 1. Now, how does one transform the system from a quantum state x into the state fx? Because one has to do computing. At the end of the day, one has to do computing. So from x, one has to go to the unitary to get to f of x. So somehow you need to pack the information of f of x into a quantum state, and that is done through the state of x. So now, using this setup, what one can do is think of a unitary transformation which takes some string, namely x and 0, and maps it to x comma x. So in this way, what happens is we are able to perform the function f of x on quantum states through the unitary, preserving the requirement of one-to-one. And in a more general setting, here I consider the supporting bit to be 0, but in general, one can think of the general oracle taking the information in the quantum states, namely ket x and ket y, to ket x and y plus fx. And each of them could be some bit strings. And with this small change, you can see that the number of inputs and the number of outputs are the same. So this is the requirement for the one-to-one map, namely the bijection, and the oracle is performing the bijection. But the only difference from the classical setup is now we are working in the domain of quantum. So going forward, we all come. So we will need some more preliminaries. You all know the Hadamard gate, how it acts on some of the states, mainly ket 0. It acts on the ket 0, the Hadamard, and you get the state which is the uniform superposition of ket 0 and ket 1, also called a plus state. And if one had to apply the Hadamard on 2 qubits, you would get now a uniform superposition of 4 states. So every time the Hadamard is applied on the ket 0 states, you get a uniform superposition of all possible computational bases. So in general, if you have n qubits and each of them are initialized to state 0, and you apply on each of these qubits Hadamards, then what are you supposed to get? You are supposed to get a uniform superposition of all computational basis states. So here, if you see, you have the x taking the Boolean strings, and the x is put inside the ket. So this is a quantum state, and you have a uniform superposition of all possible computations. Now, if I were to ask you a trick question, suppose I have this output, namely the uniform superposition, and if I were to apply the Hadamard again on this state, what do you get? Because Hadamard is its self-inverse, so you will get back the original state, namely 0. Yeah. So this we have to keep in mind as we go and explore the algorithm. So in general, now if you have a string A inside a ket, you have a quantum state representing ket A, and you have applied the Hadamard on this state, what you get is a uniform superposition of all possible computational basis states. However, the amplitude is now uh, having this term, namely -1 power a dot x. And a dot x is like a dot product, and it collects the number of ones that are present in x. The number of ones that are present in a. Right? So with this kind of a small change, what happens is you can represent the action of the Hadamard on any arbitrary string A. And the state that is corresponding to the string A is the ket. So the Hadamard acting on the state A gives you this state. And if I were to again apply, so here I've written this dot product, it takes the dot product, and it takes the components. What is -1? Okay. So the question that is being asked is this -1. So if you see,
Sir, I think the slides are not visible. Is it visible?
I got a question. I believe then it must be visible. Or Kusum says no. Okay. Let me see.
Also, the audio is little. Can you little bit scale up the audio also, sir?
Okay. Let me switch off the fan. That might be.
Maybe if you log in and log out, it will happen. Yeah. Okay.
Yeah, screen visible.
Screen is now visible, sir.
Now, are you able to see the screen?
Screen is visible, sir.
Yes.
Is it possible to put in the full slide mode? Is it possible?
Okay. One slide.
Yeah, this is good, sir.
This is better, is it?
Yeah, this is better. This is better.
Okay, then I think I will not be able to see any of you. So that's okay. If there's a question, please stop and I will then see the chat.
Yes,
Okay.
sir.
So now if you see this a dot x, the question that is asked is this: why is there a -1? So this -1 is in some sense collecting see, for example, if I put the ket 1, right, the Hadamard takes you to 0 - 1 by √2. So there is this phase factor that comes as a minus. And if you take any arbitrary string, it might have some ones, right? So you see that the one contributes to some minus here. So if there are some strings which contain one has to account for the phase factor. And if there are even number of ones, then the overall phase will get again flipped. If there are even number of ones, if there are number of ones are odd, then you pick up a minus one. So to account for that, this minus 1 power a dot x is put in place. Okay, so we go with this. Now if I have this as the output state, 1 by root 2 power n minus 1 power a dot x. Here, if I pass this through the Hadamard tensor n, what am I supposed to get? I'm supposed to get back the state A that I began with, right? So here you just, what we are basically setting up is the self-inverse nature of the Hadamard. Okay. Now that we have completed the preliminaries, now we will step on to the Deutsch algorithm. It was first introduced by Deutsch and Joza, where this was the first time we saw that the quantum algorithm performs better than the classical algorithms, and it showed that there can be advantages for solving a certain type of problem. Okay, so what is the Deutsch-Joza problem? The problem is as follows: we are given a hidden string. We're given a hidden Boolean function f, which takes input a string of bits, and it gives either 0 or 1. Okay, so if you go back to the first picture that we had, it takes n bit strings and gives out either 0 or 1. Yeah, and what we are supposed to find out is if the function is balanced or constant. So it is known that the function is either balanced or constant, and what we need to do is we have to figure out and tell that the function is balanced or is it constant. Now, what is a balanced function? Balanced function is such a function where for half the number of inputs, the output is 0, and for half the number of inputs, the output is 1. So it is balanced. And the constant function is such a function which is either 0 for all input strings, or it is 1 for all input strings. Yeah? So this is the main definition of a balanced function and a constant function. Now it is given to us that the Boolean function is either balanced or it is constant. Now what we have to do is to figure out that this function is either balanced or constant. So I'm just again reiterating, the constant functions returns either all zeros or all ones, while the balanced function returns zeros for exactly half the number of inputs and ones for the other. And the goal is to figure out whether the function is balanced or constant. Now classically, what would you do if you were to find out if the function is balanced or constant? What you will do, you'll keep giving it various types of inputs, and you will get to know if the outputs are different, then you know that the function is balanced, because it is guaranteed that the function is balanced or constant. So if the outputs are different for two different inputs, then you know that function is balanced. But you have to query. Basically, this is what is called the query model. You have to ask or query the function. Querying the function means giving it some inputs and recording the output. So we are giving all types of inputs from 0, 0, 0, all zeros to all ones. But in between, it might happen that you get two different outputs, and then at that time you can stop. Now, with this kind of a approach, then how many queries do you need to say for sure that the function is either constant or balanced? So it may happen that you have n bit strings, and the total number of n bit strings is 2 to the n. All of them are 0 in the worst case, and the next input will give you a 1. So you need to check for half the number of inputs plus 1 to ensure that your function is either constant or balanced. So you need to, at least in the worst case, query 2 to the n minus 1 plus 1 times the oracle. You have to query the oracle 2 to the n minus 1 plus 1 times. This is the worst case complexity, the query complexity. So query complexity means asking the oracle if it is 0 or 1. Now, this is the classical solution. So, for example, if a 4-bit string is given, if you check 8 of the 16 possible combinations, all of them are zeros, but there is still a possibility that the 9th input returns a 1, and therefore the function is balanced. So all you need to do is you have to check until the 9th input, which is 2 to the n minus 1 plus 1. So probabilistically, this may be very unlikely event, but in the worst case, this is what happens. And you can do like this. If you say, no, I cannot, I don't want 100% confidence. I'm okay with certain percentage of confidence. I will query only certain number of trials, and it can be worked out that if you query only k number of times, then the probability of that function being constant is like this. So if you want 100% confidence, then you need to check 2 to the n minus 1 plus 1 inputs. But if you want something lesser than 100%, you may query lesser than 2 to the n minus 1 plus 1. So to summarize, you need at least 2 to the n minus 1. I'm not at least at most 2 to the n minus 1 plus inputs to really say for sure that with 100% confidence that the function is constant or balanced. Okay. Now, so what is a quantum solution? The classical solution, the query complexity is exponential. Now, what does quantum have to offer? So what we will do is we'll invoke the ideas of reversibility and have the oracle set up in the way where you have input x and you have these ancilla qubits y getting mapped to x and y XOR fx. So with this, what happens is you are satisfying the reversibility criterion, and at the same time you are employing the function via the unitary. So this is the circuit, the quantum solution for the Dolly-Joseph problem. What you do is you can take a zero tensor n, namely the initial state, and you have these n qubits in the register. So you pass the Hadamard tensor n. So you apply the Hadamard on each of the qubits initialized to 0 state, and then this UF is the oracle that you apply on the input. So the input register is of n bits, and then they have a ancilla of one bit, and then what you do is you apply this logic x comma y getting mapped to x comma y plus fx. All right. So then you apply the Hadamard again, and then you make a measurement. So once you make a measurement, the claim of the quantum algorithm is that with one query, just one query, you can figure out whether the function is balanced or constant. This is compared to the exponential query complexity that was there in the classical. Okay, now let's go through the steps. You have 0 tensor n for going through the Hadamard tensor n, and you have 1 going through the Hadamard. So if you were to write the state at the beginning is, let's say, psi 0, which is 0 tensor n times 1. Then it goes through the Hadamard, each of them, and you have the state at position number 1 as psi 1 equal to 1 by root 2 power n plus 1 times x times y. So this x is the uniform superposition, and this one state is becoming minus state. So which is 0 minus 1 by root 2, and this root 2 and root 2 power n are subsumed in this root 1 over square root 2. Okay, so with this we have the psi 1. Now the action of the oracle will happen. That means if you have x comma y, the output is x comma y plus fx. So you have x comma 0 minus x comma 1. So here the uniform the superposition of x0 and x1 is there, and when you apply the oracle, what you get is x comma ffx minus x comma 1 plus fx, right? So this is the action of the oracle, which is x comma y getting mapped to x comma y plus fx. So now if you have x and 0, you will get, so y is 0 there, x comma 0 gets mapped to x comma 0 plus fx, which is fx, so x comma fx, and then you have a y which is 1, right? Y was equal to 1, and in this case y is 1, so you get 1 plus fx. Yeah. Now what you can do is you can cleverly take this -1 power fx out, because f of x is guaranteed to be either 0 or 1. So let's say f of x is 0, then what you'll get 0 minus 1, 0 minus 1, yeah. And if it is f of x is 1, then you get 1 minus 0, right? So depending on the value of f of x, one can cleverly take this out as -1 power f of x times x times minus 1, x times the minus 2. So this is what is called as the phase kickback trick, which is done typically using the oracle and the answer, which takes into account the answer. So now f of x is either guaranteed to be 0 or 1. You have x times minus 2. Yeah. Going forward, now at point 3, you are again applying the Hadamard. So now you apply the Hadamard on the first register and go through this. Now this is the overall, the final state now. And if I were to calculate the, if I were to measure this, I had to look at the state at the time before the measurement. So this state psi3 is the state before the measurement, and you have this joint state. And looking at this, if I want to calculate the probability of measuring an all zero string, so what do I need to do? I need to put y equal to 0 and calculate what is the uh, probability of finding an all zero string, right? So if I were to calculate the probability of measuring an all zero string on the first register, it comes out nicely. You just have to put y equal to 0. So this thing x dot y goes away, and all you have is -1 power f of x, and you're summing it over all possible strings, n-bit strings, and you get this. So if the function is balanced, that means for half of them it is -1 and half of them it is +1. So overall the summation is 0, right? So that means the probability of measuring an all zero string is 0 if the function is balanced. And if it is constant, then the probability is equal to 1, because everything is, you're summing over all n-bit strings, and you're summing this, each of them are equal to 1. So this probability of measuring an all zero string is equal to 1 if the function is constant. So in one shot, depending on the measurement of the first register, you are able to say that the function is balanced or constant. If the function is, if you get a measurement of an all zero string, then that means the function is constant. And if you get some other string, non-zero string, then you know that the function is balanced. Yeah, is this okay, everyone following so far? I'm just checking because I can't see you. So far, everyone is able to follow. Shall we go forward? Okay, I'm assuming we can go forward. Okay. All right. Can you see my screen? So why does this work? I think you are all clear. What happens is you have this Hadamard acting on the all zero string. It gives you the uniform superposition. And after the action of the oracle, you have this particular state. And if the function is, if it is constant, then you get back the all zero string. If it was balanced, then so some of them will become minus, and then they will all sum to. So the probability will be 0. The probability of measuring an all zero string will be 0. You'll get the probability of some others. You will have a non-zero probability of some other string. All right. So this is what I meant with the oracle. The sum of, so half of them will become -1 and half of them will become +1 and so on. So this is what I meant, that if you measure an all zero string, then that means the function is constant, and if it is some other string, then it is balanced. Okay, so I think I'll just go forward some example. Now I have this Bernstein-Vazirani algorithm. The Bernstein-Vazirani algorithm is like a similar sort of a algorithm like Deutsch-Jozsa, but a small extension. of the Deutsche. Okay, so the Bernstein-Vazirani, what is the problem here? It is exactly the same as the Deutsch-Jozsa. However, you are guaranteed that the function is like a dot product. So what you're doing is we are given a function. It again gives either output is either 0 or 1, but the function output is dependent on some hidden string s, right? And this hidden string is s is such that your output is dependent on the hidden string s via this notation. So it is like a dot product of x and s. So whatever input you give x, it takes a dot product with this hidden string s, and it gives you either 0 or 1, right? Because it's a mod 2 uh, computation, right? So s dot x is a mod 2 operation. So either you get a 0 or a 1, and this is a specialized structure imposed on the Oracle, right? So it has some hidden string s, and whenever an input x occurs, it takes a dot product and spits out the output as 0 or 1. And our goal is to find out the hidden string s, right? Now here also there's a, for example, the classical reversible circuit. You will have this x and the ancilla 0, and you have this function f, and you have x comma 0 plus fx, which is namely s dot x. Yeah. So one has to look at now the classical solution. What is the classical solution? If you were to ask uh, how many queries will you be able to find out this hidden string s, what would be your solution? What will you give as inputs to figure out the string s? You will give 1 followed by all zeros. If you give 1 followed by all zeros, this will reveal the first bit of s. If you give 0, 1 followed by all zeros, this will reveal the second bit of s, and so on and so on. So this tells you that the query complexity is precisely little n, right? Small n number of times you need to query the oracle, and every time you query the oracle, you are revealed the particular bit of the hidden string s. So in the worst case, you have to query the oracle n times. Now, what does quantum have to offer here? Quantum, again, like the Deutsch-Jozsa, can do it in one shot, which is the just one query. Within just one query, you can figure out that the function is what is the hidden string is. Right? So this is the claim of the quantum quantum algorithm. So again, I will revise this, why we need it. So you have the Hadamard applying on 0, you get the ket 0 plus ket 1 by root 2. And then on the ket 1, it is ket 0 minus ket 1. And on the ket 0 tensor ket 0, it gives you the uniform superposition, and so on and so forth. If you have the all zero, zero string going into the Hadamard gate, it gives you the uniform superposition of all computational basis states. If you apply the Hadamard on this state, the superposition of all possible computational basis states, you get back the zero tensor n. Right? So for an arbitrary string A, you get minus 1 power a dot x. So this is the importance now. So I again reiterated because sometimes we miss the importance of this formulation. So I have again reiterated. Okay, so we'll use these ideas. Now, suppose, so all that we need to do is, to solve this problem, we need to set up a superposition of minus 1 power s dot x. If we somehow set up this superposition, then pass it through the Hadamard tensor n, what do you think will be the solution? What will be the output state if we pass this state through a Hadamard tensor n? We will get the state s. So because you just recall this, right? We just mentioned if you have 1 by root 2 power n minus 1 power a dot x applied on Hadamard. So if you apply the Hadamard on this state, you get the string a. So here, if we somehow are able to get this minus 1 power s dot x, the hidden string s, and the state such as this, we pass the Hadamard, we are going to get the state s, and if you measure the register, you are going to get s with probability 1. Yeah. So now the whole problem rests on, is pinned down to creating this superposition state, this minus 1 power s dot x times x. Okay, so now how do we get that? We'll come there now. Using a quantum computer, we can solve this problem with 100% confidence after just one call, just one query to the Oracle, and you're done. So this is the solution. It looks exactly similar to the setup of the Deutsch-Jozsa. And if you recall, in the Deutsch-Jozsa, you had all zero. The first quantum register was all zero string, and then the ancilla was 1 qubit, and then you had the same circuit. So the circuit is exactly the same, and we want to see if this circuit can solve this problem. And the claim is yes, it can solve the problem of the hidden string S. So first you do is initialize all the qubits to 0. The first register, initialize it to the 0 state, and then pass the Hadamard and query the Oracle. So these are the three things, and then you do the same thing, like you apply the Hadamard on the first register and then measure. So these are the steps are exactly the same as that of the Deutsch-Jozsa. Okay, so now let's look at if you have, again I'm reiterating, a tensor. So you see you have the ket A and you apply the Hadamard tensor n on the ket A, you get this. So let's go with the flow. The first register is in all zero string. So if you apply the Hadamard, you get the uniform superposition of all computational basis states. And then in case you have A to be all zero, then you have this minus 1 power A dot x disappears. So you have the uniform superposition of all possible computational basis states. Right now, if you see, what we want is essentially this x on which the function f acts. Somehow we should be able to encode and get the state minus 1 power s dot x times x, because this will be useful in our solution, because we know if we get a uniform superposition of this particular minus 1 power s dot x times x summed over all x, we can apply the Hadamard tensor n on that, and you can measure and get it. So let's go over the steps. What we need to do is get this state somehow. So can you get that? Let's see that. So the circuit, if you recall, you had the x comma 0, and when you apply the oracle, you get x comma 0 plus fx, and through the phase kickback trick, you can get back that minus 1 power s dot x times x. So the circuit remains exactly the same, and you get this minus 1 power s dot x as the state of the first register. And again, if you apply the Hadamard tensor n, you get the state S, and which you can measure. Which you can measure, and at the measurement outcome, you get the string S with probability 1. Right. So let's work it out through an example. Initialize the first register to be all 0, and then pass the Hadamard tensor 2, because there are 2 Hadamards and 2 qubits. You get the uniform superposition of all 4 possible states. And on this, you apply the oracle. You have the x and the 0. The first register is consisting of 2 qubits. The second register is consisting of only 1 qubit. And you apply the oracle, x comma y, it becomes x comma y plus fx. And because f of x is either 0 or 1, you can take out in terms of the phase kickback, you get minus 1 power f of x, but that f of x is actually s dot x. So it's precisely this. And once you apply the Hadamard again on the first register, you get this. So if you measure, you get this string S equal to 1. So it's exactly the same as that of the Deutsch-Jozsa. And you can work out an example with 3 qubits and show that, if you can apply the string S, the secret string S is equal to 0, 1, 1, and think how you will make the oracle for this case, right? What you need is to take x and apply minus 1 power x dot this 0, 1, 1 for the case of three. So work out this example and see how we will realize this circuit that takes x to minus 1 power x dot s times x. So think about it. Okay, then comes the Simon's algorithm. So this is another nice algorithm where here we can say that there is exponential speed up to solve a certain problem. The classical problem takes exponential time, and the quantum solution takes when I'm saying time, what I mean is that in terms of the query complexity, the number of queries. So that is our benchmark, because we need to compare apples with apples. Yeah, and we need a common framework. So query complexity is the type of benchmark or the metric to study performance or compare quantum algorithms compared to the classical algorithms. So now we will set up the Simon's problem and what it is, and then see how the quantum solution is like. So the Simon's problem is as follows. You are given a function which is guaranteed to be either a one-to-one function or a two-to-one function. What does this mean? One-to-one you already know. Two-to-one is there are two inputs which map to the same output, right? So this is the two-to-one function. And the two-to-one function, I have just given you an example. F of 1, this is a one-to-one function. F of 1 is 2, F of 2 is 3, F of 3 is 4, F of 4 is 1. So for different inputs, you have unique and distinct outputs. And this is an example of a one-to-one. And the number of inputs is same as the number of outputs, in this case 4. However, two-to-one mapping would be 1 and 3 are mapped to 2, and 2 and 4 are mapped to 1, right? So there are two inputs which are mapped to the same output. Yeah, I hope this setting is clear. And this 2-to-1 mapping is according to the hidden string. Sorry about that. This 2-to-1 mapping can be written nicely in terms of mathematics. So there is this hidden string B, and what we have to do is so there are two inputs which give you the same output. No, so x1 is equal to x2, right? There are two inputs, and it is guaranteed that the two inputs are related to each other via the secret string S, right? So the two strings which give you the same output, x1 and x2, are differing from each other by the string S. What I say by differing is this XOR operation. You can write the two inputs in a relation such as this. So x1 XOR x2 is equal to x. So x1 and x2 give you the same output, and these x1 and x2 are related to each other via the S, right? So they differ by S. This is what it means. And the goal is to find out the hidden string S. So if I were to ask you in the classical setup, how many queries do you need to find out the hidden string is? You want two inputs to give you the same output. So what you will do, you'll keep querying the oracle. You start with all zero string and the next string and so on. And the moment you see there are two outputs that are same, right? Then you will pick the two inputs that led to the same output, and you will subtract the two, or basically apply the XOR operation between the two inputs. Then you get the string S. Right? If the string S is all zero string, then it is not a 2-to-1 function, it is a 1-to-1. Because f of 1 x1 equal to f of x2 and S is 0 means it's a 1-to-1 function. Okay, so now what is the classical solution? If we want again 100% confidence, we need to again check for 2 to the n minus 1 plus 1 number of inputs, because for the first 2 to the n minus 1 inputs, the outputs may be all differing, and the next input might give you collision. What I mean by collision is there are two outputs that are same. You keep monitoring the outputs, you keep giving the inputs, you keep checking the outputs, and you may have to go all the way to half of them plus 1, where you might see collision. What I mean is two outputs that are same. You might have to wait until the 2 to the n minus 1 plus 1th number of input. So this is the worst case complexity in terms of the for the Simon's problem. Okay. Now, what is the quantum solution? The quantum solution is that here you can solve this problem in order of n number of queries. So basically, instead of the exponential complexity, here you have order of n complexity. So the solution, what is the solution? So first we need to set up a superposition of some string r and r plus s. See here s is the hidden string. So if we can get somehow the superposition of r and r plus s, and then we do certain things, namely you apply the what you need to do is you apply the Hadamard tensor n. That is what is called as Fourier sample. So for this state, somehow you need to create this state, and on this state you apply the Hadamard tensor n. And once you have applied the Hadamard tensor n, what you do is you measure, and the measurement is say y. The y string that you get, it satisfies s dot y equal to 0, right? So what you are basically doing is you're measuring, and you're solving a system of linear equation, right? Every time you make a measurement, the string y, it satisfies s dot y equal to 0. So you hope to get the string y to be linearly independent of the previous measurements. So what you do, you keep setting up, you keep the oracle, the circuit, you keep running the circuit and you keep measuring, and every time you get a different y, it helps you to get closer to the solution or finding out the string s, because you're solving for s, no? So you are solving a system of linear equations. So every time you make a measurement y, you get the string y which satisfies s dot y equal to 0. And recall s dot y is the inner product which was mentioned a few minutes back. Okay, so now you repeat this n minus 1 number of times. If you repeat this n minus 1 number of times, then you hope that maybe you may need a little bit more number of times, because all you need is n minus 1 linearly independent set of equations. So until you get, you may have to keep performing the measurements, but it is not it's not going to be very a large number in terms of the querying, in terms of the measurements. So you keep doing it until you get n minus 1 linearly independent equations. Once you get it, you will solve for s, because this is all you need to do is find out the string s, right? So the system of linear equations that you get, you need to solve and figure out the string. Okay, so this is what the algorithm is. Now what remains is, how does one set up this superposition, right? This r and r plus. Okay, so that we will study now. We will have this circuit, namely the first register consists of n qubits, the second register also consists of n qubits, and all of them are initialized to the gate 0 state. Okay, if you compare this with the you compare this with the Deutsch-Josa and Bernstein-Vazirani, it's looking very much similar. Just that the second ancilla, it's not going through any Hadam. You have 0 tensor n, you have 0 tensor n. You have n qubits, you have n qubits. So total, you have 2 n qubits. The first n qubit register goes through the Hadamard tensor n, and then you apply the oracle, right? The unitary that performs the action of the oracle, namely the function f. You have the unitary version. If you carefully remember, if you observe, we have this x comma y getting mapped to x comma y plus fx, right? So the setup is precisely the same, where y is 0, all 0 strings. And then what you do is, after the oracle, you measure the second register, and once you do a measurement, then you will get to that state r and r plus s, that what we claimed here. No, you have to create the superposition of 1 by root 2 r and r plus s, where r is some random string. That happens if you make a measurement here. And then from the previous slide, once you have this random superposition, r and r plus s, you apply the Hadamard tensor n, and then you make a measurement. So this measurement y, the measurement outcome say y satisfies y dot s is equal to 0. And you keep running this circuit again and again until you get n minus 1 linearly independent set of equations. And once you have those, you solve for s. So just recall, you have x and a, and the oracle UF acts, you get x comma a plus x, right? So this is precisely the setup. Here x is an n-bit register, a is an n-bit register, and you take x and a, it maps to x and a plus fx. In this case, if you see, a is 0, all zeros, right? In the second register is all zero strings. So the first register is say x comma 0 tensor n maps to x comma fx. This was precisely the same that you saw. Similar to this you saw in the first two algorithm, Joyce-Joza and the Bernstein-Wasserman. Right? So this is the typical setup, right? X comma y getting mapped to x comma y plus x. All right. So now let's work through the steps. How does one unearth the string s? You have the initial superposition. So for that, what you do, the first register is initialized to all zero string, namely the 0 tensor n, and the second register is also mapped to the all zero string. Then you apply the Hadamard tensor n on the first register, right? So with that, you will get the uniform superposition of the all possible computational basis states on the first register. So I've written that as 1 by root 2 power n summed over all x times x. And then the contents of the second register is all zero string, so 0 tensor. Are you following so far? What is happening? Maybe I will take a pause here just to see if everyone is following. Are you following?
If anyone has any doubts, you can post in the chat box.
Okay, so I here I
Yes,
can see
Avi.
that
Yes,
they are
yes.
able to follow. Okay, okay, all right. So now let's continue. We have the uniform superposition on the first register, and then you have 0 tensor n on the second register. Right now, if you now apply the oracle, what happens? You have x and 0 that gets mapped to x comma fx, right? Because 0 XOR fx is fx. Yes. So let's see what happens. You get the x comma fx after the action of the oracle uf. So at timestamp 3, you have x comma fx emerging. Now, if you were to measure the second register, what will happen? It will be some outcome, no? Some f of r. Let's call it some f of r, right? So if you measure the second register, you see this x comma fx. So x and fx are tightly coupled. Whatever happens to f of x, it is bound to impact the contents of the first register, right? This is basically the phenomenon of entanglement. So the first register and second register are coupled now. They are entangled via the oracle, right? The oracle induced this kind of coupling for this entanglement, right? So if you measure the second register, it might be some, you might get some value, right? So of the f of x, and but because the function is such that it is a 2-to-1 function, so if you get f of r as the output, so I'm saying x is equal to, like I'm saying f of x is equal to f of r, right? Some string, some r is some random string, and if you get some arbitrary string r, namely the f of r on the second register, what are the contents of the first register? It better be r and r plus s, right? Because it is those two inputs. If you recall, let me go back. It is these two inputs. So for example, r and r plus s, right? 1 and 3 are giving the same, sorry, here. So 1 and 3 are giving the same output, no? So your f of r in this case is say 2. Then there are two inputs that lead to the same output, no? So so your f of r is we say 2, and their r and r plus s are what, 1 and 3. So 1 and 3 are the two inputs that give you the same output, 2, right? So your f of r is say 2, and the inputs are r and r plus s, namely 1 and 3. So there are two inputs. If you go back, let's see this. What we wanted is a superposition of r and r plus s, and precisely that is happening. If you measure the second register, you get some f of r, and because this is a 2-to-1 function, there are two inputs, namely r and r plus s, because the two inputs differ by s. No, in the setup of 2-to-1 function, the r and r plus s are the ones which lead you to the same f of r. So now you know that there are two inputs that led to the same output, namely the two inputs are x and y, and the y is basically x plus s. So I'm just writing it as x and x plus s. So once that is clear, what you do is you apply the Hadamard tensor n, and you make a measurement. So once you apply the Hadamard tensor n, you know that formalism. On any string a, you apply the Hadamard tensor n, you get a dot x summed over on x, right? So with this, you get an output. You will be able to, if you make a measurement, you will see an output only if these two are equal. See, if they are of opposite signs, you don't see the state z, right? -1 power something can be either 0 or 1. So y dot z can either be 0 or 1. So if you have to have a non-zero value, right, they better be equal. Then only you will be able to measure the state z. If they are of opposite signs, they cancel and you don't get that particular z. So it is better, you will see an output only if x dot z is equal to y dot, and the two differ by s. So this is precisely the solution. So you remember s dot z equal to 0. I spoke of s dot y, I mean it's the same. So when you make a measurement and you get the string s, it satisfies s dot z equal to 0. So now this is one particular measurement. Again you do this, you might get a different z, and again you might get a different z. You keep doing until you get linearly independent set of equations. So if you get linearly dependent, you again repeat, keep doing it, but you may not have to do it in a like large number of times, and it's just order of n. And once you get these in n-1 linearly independent equations, you can always solve. So here you get s dot, say in the first iteration you get z dot 1 equal to 0, then s dot z2 equal to 0, s dot in the n-1th iteration you get n-1 z, and all of them are n-bit strings. Each z is an n-bit string. I've just labeled them as 1, 2, and -1. So once this happens, you have a system of linear set of linearly independent set of equations, and you solve for s. And once you solve, you're home, right? This was the main task of finding the string s, right? Given this 2-to-1 function, your goal was to find out the string s. And by solving this system of linear equations on a classical machine, on a classical computer, you can get these strings. Okay. So with this, we complete the Simon's algorithm. Okay, now we come to the Grover's algorithm, right? So this is the last algorithm, and in case we have some time, we can take questions, or I can give you some more motivation as to what is happening. All right. So in the Grover's algorithm, we've seen that there are some advantages in using the quantum algorithm over the classical ones, right? So we saw three algorithms, namely Deutsch-Joseph, the Bernstein-Vazirani, and the Simon's algorithm. Similarly, there is this quantum computer has an advantage over the classical computer in searching the databases. So this is a database search problem. It's an unstructured database, and you want to look for a particular entry in the database. Classically, there is some complexity. The quantum, what it promises is that you can speed up the search process and your query complexity in this case is root of capital N. If capital N is the number of items in your database, unstructured database, then you need a root of capital N number of queries to get to that um, chosen item, yeah, that item that you want to pick or you want to search for, right? The marked item. Okay, and what we use is in this Grover's algorithm is a trick called the amplitude amplification trick. So the amplitudes keep changing, and the amplitude of the solution, right? The solution in this case is the entry that you're searching for. The amplitude of that is somehow made, it keeps growing, and after a certain number of iterations, uh, if you make a measurement, then you are likely to get the marked entry with good probability. Okay, that is the whole setup, and this was, found by Love Grover, an Indian. So it's a matter of pride that he found this Grover's algorithm. Okay, so the setup is as follows: you have some number of items in the database. Let capital N be such that it is equal to 2 to the n, because it can nicely correspond to the n-qubit state, right? One can map it to an n-qubit state, and the number of amplitudes for an n-qubit state is 2 to the n. Right? So now you have these many number of items, and what you have to do is you are supposed to search for a particular entry that is marked, right? So I've just marked it as some W or omega, and you're looking for this particular entry, right? And you have a large database, and you wish to find out this particular item which has a certain type of a unique property. And once you find this, you can call this as a winner. Okay? Now, each of the item in the list as a box of some particular color, and only this winner or the marked entry is marked purple. Rest of all of them are gray. Right? So basically, you're looking for the purple entry, and rest all of them are the gray entries. Right? So now to find the to solve this classically, what would you do? You will check each and every entry, right? If there are capital N number of items, you will go and search for each entry and check if it is purple, right? So the complexity in this case is capital N, right? You will have to ask, you have to open the oracle, or you have to ask the oracle, is it purple? Is it purple? And you have to do it for all capital N number of them, right? So the complexity is capital N in the worst case, that you might have to wait till the end. Perhaps the last entry is the one that is marked, right? But on an average, if you keep going randomly, you might need half the number. Like you may have to query n by 2 number of items. Or in other words, you might randomly pick some n by 2 items, and you might have to check, is it purple and so on. On an average, if you go randomly, you will find the marked entry, and the query complexity is precisely n by 2. So you will need to look for the purple box n by 2 number of times on an average. Right? This is still large, right? Now the Grover's algorithm, it promises root n number of the order of root n query complexity, right? To search for the marked entry. Sorry, it's late in the evening. Yeah. So now we have this marked entry, and the Grover's algorithm uses the amplitude amplification trick and requires root n number of steps. This quadratic speedup is indeed a substantial time saver for finding the marked entry for marked items in long lists. Right? Additionally, the algorithm does not use the list's internal structure, which makes it generic. Right? Here, there is no structure that is assumed. It's an unstructured database, and that is why it immediately provides a quadratic quantum speedup for many classes, where you need to perhaps search for the item. Yeah. Okay. So now in the algorithm, there are two phases. The The two phases are namely the query phase and then the amplitude amplification or the inversion about the mean phase. Okay, so now let's look at what is this query phase. Yeah. So for example, now we will need an abstraction of connecting it to qubits, right? So for example, if you have 3 qubits, then our list is consisting of 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way till 1, 1, right? States that are 0 through 7. Now, the Grover search or the Grover's algorithm solves the oracle that adds a negative phase to the solution state. So this is the query. So if the marked entry is, say, for example, 0, 1, 0, the query phase, what does it do? The oracle is used for the query phase. If it is marked, it gives you a phase, or if it gives you an amplitude of -1. Basically, it gives you a negative phase to the marked state. Right? So this is what we have to do. In other words, you have this oracle UF acting on X. It is equal to X if X is not equal to W. And whenever it is equal to W, the purple entry, right, the marked entry, you have a phase of -1, right? It inserts a negative phase to the marked entry the moment X is equal to W, right? This is the first phase, namely the query phase or the use of the oracle. This is what the oracle is doing, right? Uh, it takes input X and it gives you minus get X if X is equal to W. If it is not, then it leaves the state unchanged. Yeah. So this is the action of the oracle that is required. Now, how does the algorithm work? So before looking at the list of items, we have no idea where the marked entry is, right? So what do? You just start with a random guess. What do you mean by random guess? Your initial guess can be any location, right? And what would be your state that corresponds to that? It will be some uniform superposition, right? So your initial guess is a uniform superposition of all possible locations X, right? You're basically checking if this X the entry is purple or not, and your initial guess is it can be anywhere. So your first guess would be take a superposition of all possible locations where the purple entry can exist. So how does one get this uniform superposition? Through the Hadamard. So you set up the uniform superposition via the all zero state, right? The all zero strings, you consider a state all zero tensor n, pass it through the Hadamard tensor n, you get the uniform superposition. So now if you were to make a measurement, you are likely to succeed with probability what? 1 upon n, which is quite low. N is very large. The probability will be just 1 by n, right? This is just a uniform state, and you're guessing, your purple color to be at certain location X, which is equally likely to be anywhere. So what we want to do is we want to increase the amplitude or the probability of finding the purple entry, right? How does one do? The first step is we are making a general guess, and we are likely to succeed with probability 1 by n. We want to somehow increase this probability of success. The probability of finding the marked entry, want to increase the amplitude. So if you increase the amplitude, the probability will be the mod square of that, the amplitude square, and you want to increase this probability in such a way that after sufficiently large number of circuit size, then you are getting the marked entry with fairly good probability, right? So now let's look at it from a geometrical point of view. Okay, so if you see from a geometric point of view, this Grover search is a very simple uh, algorithm to learn, right? So what we need to do is we have this W, which is the marked entry, and we have all states that are orthogonal to the marked entry, which is W per, right? Now, in the worst case, the marked entry could be only one, right? Uh, Imagine out of this large database of capital N, only one particular entry is the marked entry. right? So you will keep the marked entry in the y-axis and the non-marked entries or the bad entries in the x-axis. Now, together, because they are orthogonal to each other, one can describe any state as using this W and W per, right? So we are choosing a two-dimensional vector space, namely W and W per, and we are writing any arbitrary state in terms of this W and W per. Okay. So our initial guess, which is the uniform superposition state, can be written in terms of W and W per. All right. So what do? We use a procedure called the amplitude amplification, which enhances the probability of finding the marked entry. What do? So look at what we do is there are two steps, namely the query phase, and then we have the phase inversion phase, also called as the inversion about the mean. So if you keep doing these two steps again and again for roughly root n number of times, namely order of root n, then after that, if you make a measurement, then you are likely to find the marked entry. So this is the whole essence of Grover's algorithm. You run these two phases, the query phase and the inversion phase, approximately of the order of root n number of times. And after though if you're doing these two steps again and again, and then you make a measurement, then you're likely to find the marked entry. Okay, so I will give you this was first picture was the geometric picture. Now I will give you the picture of in terms of the amplitudes. Consider an example where in the beginning my guess is uniform, right? So I'm taking a like a 2-qubit state. I have 4 outcomes, and each of them are equally likely, and the amplitude of each of them is 0.5, right? So you have 1 by 2, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And the probability of each of them is 1/4, right? 0.5 whole square is 0. Now, in the first step, what you do is you query, right? Query the oracle. So let's say the marked entry is 2. You invert the phase. So the moment the oracle sees 2, it inserts a phase of -1. So your amplitude, which is 0.5, becomes -0. Now you calculate the mean. What is the new mean? You have 0.5 plus 0.5, and then you have minus 0.5, and then you have 0.5. So this is 1.5 minus 0.5, which is 1 upon 4, which is 0.25. So this is the mean. And now what you do is you invert the states about the mean, right? So I've mentioned the mean in these dotted lines as 0.25. Now if you invert, you find a reflection about this dotted lines. So this will become 0, right? I've shown it here. And the second point becomes 0. And the amplitude of entry number 2, you have to find the inversion about the mean, right? The mean is 0.25. So if you invert about the mean, then you have to go 0.75 above the 0.25. You find the mean above, if you want to find the reflection about the mean is point at a distance of 0.75 from minus 0.5, correct? So if you invert the mean, you have to go 0.75 up, which is precisely this. So it is overall equal to 1, and then the third entry is also 0. So now you see, if you were to measure now the quantum register, you are going to find the marked entry with probability 1. Right? So this is the amplitude amplification step, and the first step was the query phase. The second step is the amplitude amplification phase, right? So this is quite intuitive to follow via the two steps, namely the okay. Now, where are we? So what are the steps? First step is to initialize using the Hadamard. You initialize all the n qubits, apply Hadamard on all of them, and you have the uniform superposition of all of them. Your guess is equally likely. And then you apply the query phase and the inversion phase, and you make a measurement. After you run this for order of root n number of times, you are sufficiently confident that your probability will be you are going to find the mark rate. So now the implementation, the geometrical proof. So what you do is there are two steps to be performed. First is this step, right? So whenever you have x is equal to w, you introduce a phase of minus x, and whenever it is not equal to w, you don't do anything. And what you need to do is implement this function as a unitary, which takes x and a minus. It takes you to minus 1 power f of x, x times minus. So this is precisely the phase kickback trick that we saw, right? So let's sort of check the validity of this claim. So whenever x is equal to w, you see that f of w becomes it picks up a minus phase, right? Uh, u of x, it gives you a minus x whenever x is equal to w. And then the next step is this is the query phase, the uf step, and then the inversion about the mean. The inversion about the mean is done via reflection about this the guess, right? The initial guess. The initial guess was S, which was the uniform superposition state. Then you make a reflection about this state S, and for that you need to implement the unitary UG. So this is the query phase oracle, and this is the reflection about the mean unitary. So let's look at it from the geometry point of view. Initially, you have the guess to be S, and your W and W perp are the are the form a two-dimensional vector space. So here you have the W perp, and then the W. Your guess is the state S, and it is making an angle of theta. So first what you do is you invert or you create a reflection about the W perp. So your S becomes, you apply the UF, and it goes somewhere here. It makes an angle theta, and you're reflecting about this W perp. So S becomes UFS, right? This is the first phase. And the second phase is the inversion about the mean, which is this is the S. So you reflect this state about the state S. So you go 2 theta from here. So overall, if you see, your initial guess was at an angle theta from W per. Now, after one round of query and the amplitude amplification, we are 3 theta away from W per. So if you see from geometrical point of view, from S, we are going towards the W, right? The W is the marked entry, and geometrically, if you see, I'm going closer and closer to W. Yeah, but in general, this theta is very small, so I'm just making it, sort of zoom this to see the thetas cleverly or properly. Right? So if you keep doing this again and again, every time the inversion about the mean and the querying phase overall keeps adding an angle of 2 theta and so on. And after sufficiently large number of these two phases, you are closer and closer to W. So if you make a measurement, you'll be almost very close to W. This is the whole idea. Now if you repeat, so I'm just writing this mathematically. Initially the angle is theta, and after R rounds of query phase and the amplitude amplification trick. So I'm assuming that I'm doing these 2 steps R times. So every time you have this angle 2 theta getting added, initial angle was theta, and what you want is this angle to be equal to pi by 2, right? When this angle becomes equal to pi by 2, you're exactly sitting at W, right? You want your S to go to W, right? So once you have this, so if you want this to be very close to pi by 2, and initial state S was 1 by root 2n times W plus this W per. So this state was written in terms of W and W per, and one can think of this as sine theta, cos theta. And since theta is very small, because you see this sine theta is 1 by root 2 power n, and if n is very large, this theta is very small, so sine theta is very close to theta, and one can just rightly plug in that you need order of root n number of steps, and root n by 4, but it's basically order of root n. So roughly after r steps, your S becomes very close to W, the Mach entry. And once you make a measurement, you're home, right? I think this is a good time to pause. Do I have 1 or 2 more minutes, or should I end? I can just show the whole thing again in the amplitude space. If I'll just take 1 or 2 minutes. Can I do that?
So yes, sir, you can proceed, sir.
So just let's look at the same thing. So I've given you the geometrical picture. Initially, your guess is S, and it is inching closer and closer towards W. Now we will see the same thing happening in the amplitude, amplitude language. You have the amplitude, and the marked entry is W. You have capital N number of items. So in the first phase is the inversion phase. So marked entry, it flips. You have a minus sign, right? And then you calculate the mean. And once you calculate the mean, you invert about the mean. So you see the amplitude of the marked entry has increased and the amplitude of the other entries have reduced. So you keep doing this again and again. So first the amplitude is 1 by root n, then the mean is slightly below 1 by root n, and your amplitude has increased from 1 by root n to 3 by root n, right, of the marked entry, and then it becomes 5 by root n, and so on. So that is the whole thing, 5 by root n, 7 by root n, and so on. And after sufficiently large number of root n number of times you measure, you're going to be very close to the marked entry. So I think with this we can, I think it's a good time to close, because if you want the math I can go, but I think it's a good time to sort of pause, and if there are questions I can take them. If not, let me.
So there are a few doubts on the chat box.
Okay, let me see. So are there any questions? Could you please give an application to compare Grover's algorithm with traditional search algorithms? How can we explain to our students in terms of search comparison? Yeah, so exactly when students ask us, how does one compare? So the metric to look for is the query complexity, right? We have to querying basically it's like asking the oracle. If you have a classical machine, you cannot look inside the machine, inside the box. You can only query. What does query mean? You give it some input, you record the output. Give it the input, record the output, right? So classically, if I were to search for this particular entry, I need to ask. So imagine I have a lot of boxes and I need to find in which box a particular item is. So I need to open every item, right? And in the worst case, you have to search or open all the entries, right? That's the capital A. But in the quantum case, you are guaranteed root n number of times. So that is something that you have to compare. When the students ask, you have to use the metric of the query complexity. So, and one can look at, one need not see this, from a point of view of what is the point, where can I apply and all that. This might be used as a subroutine somewhere else. It might be a part of a bigger algorithm where you need to quickly search for a particular entry, and everything can be automated, right, in terms of programming. So you can set up and search for a particular query, and in the classical machine your function might take longer time, but in the quantum, if the subroutines are written in such a way that one can program and find a particular entry, and this Grovers can be a subroutine inside a big algorithm which is solving a mega problem, and that is where this might be helpful. And how about this? How about running this algorithm on real hardware against running them on a simulator? So see, this is where one is limited by the resources. See, if we have access to some big computer in terms of the number of qubits, then we can run those on those machines. At some point of time, one will be, exhausted of the classical, and you can only go to certain number of qubits on a classical machine. See, if somebody is a very rich person, he might buy, like a very high-end RAM and all that, GPU and all that. But still, we are limited in terms of what we can actually, be advantages, where we can see an advantage. However, once we have the quantum hardware, then there are no limits. Then we can, if you have like large number of qubits, say 100, 50 or 100, logical, actually, I mean logical qubits. So if there are 50 to 100 logical qubits, then I think it will be very fast, it will be very good. And that is the kind of, like a dream project. Any quantum computing person would be looking at, uh, thousands of logical qubits. Then we can have like a very good advantage. And how is the security of public key cryptographic algorithms after the advantage of uh, security of public key cryptographic algorithms after the advent of Shors and other? So see, these Shors, what people are doing is they are studying what is called as post-quantum cryptography, PQC, and they are saying that these are the algorithms or these protocols are like they cannot be cracked by a quantum computer, and that is why they are relying on what is called as this post-quantum cryptography. This is their way of uh, managing the cryptography scenario. This is their modus operandi. This is how they are working. uh, but still Shor's algorithm is not implementable in the sense of, as of now, in terms of the hardware. You will need many logical qubits to actually execute Shor's algorithm. People are refining the technology, how to make good qubits and logical qubits. Once we have very good logical qubits and you have thousands and 10,000s of those, then the Shor's algorithm can be actually beneficial, and that is when the advantage can be seen. And see, if you see that as a threat, the classical people, they are proposing what is called as a post quantum cryptography, PQC. So you might want to study that PQC. This is how the reaction is of classical cryptography. Classical cryptography. So any more questions? I hope that was answered. Hiren Patel and I am Sandhya, Dr. Sandhya.
So thank you, sir.
Thank you.
Thank you a lot, Dr. Ankur, sir, for your detailed explanation on the various algorithms. And I'm very sure that the participants have gained a lot of information through your lecture, very informative lecture. And thanks for accepting our invite and helping us for the support towards this FDP. On behalf of the management of KCG College of Technology and the entire organizing team of this ATAL-sponsored FDP on quantum computing, we extend a heartfelt gratitude for spending your precious time with us and the participants. Thank you so much, sir. Thanks.
Yeah, thank you. Thank you so much for the invitation. I hope it was useful. Thank you again.
Yes, sir. Also, our next speaker is Dr. Alain Chan from France. And sir, have you joined online? I could see that you are.
Yes, thank you for having me. Should I introduce myself or you want to do it?
I'll be introducing you, sir. Can we just check your audio is very clear? Can you please share the slides one so that we can check the visibility also?
Sure, I will share my screen right now. Okay.
Ankur, sir, I think you need to. Okay, it is done. Yeah.
Okay. So can you see my screen?
Yes, sir, it is very clear.
So I will switch
I
to
will
the.
just introduce you for a second and then we can start the session. So I'm very glad to invite Dr. Alain Chan from France, and very much happy to see that Sir has accepted our invite to take a session on this FDP, AICTE ATAL-sponsored FDP on quantum computing and quantum machine learning applications for sustainable solutions. So let me give a brief note about Sir's achievements.
So,
Dr. Elaine Chan is the president of Market SaaS, a member of QEDC and QUIC, founder of Quantline SASU and Align Quant LLC, offering management consulting and AI services. Sir is the advisory board member at North America Technical Institute, Virginia, USA. Sir is very famous for his very interesting lectures, and he is a Quiskit advocate and a senior member of the IEEE. Society affiliate of the American Chemical Society ACS, member of the American Physical Society APS, and the Quantum Security and Defense Working Group QSECDEF. Sir is a co-author of Quantum Chemistry and Computing for the Curious. The book is quite famous among the enthusiasts of quantum chemistry. Sir has illustrated a lot of Python coding and Qiskit coding in this book. Sir is also one of the authors of Quantum Permutation Pad with Qiskit Runtime in Fenman with Springer Publishers. Sir has been the keynote speaker for various international conferences, including a keynote speaker at the IEEE 14th International Conference on Communication Circuits and Systems at China during 2025. Sir has been a panelist at the QEDC Quantum and AI Use Cases panel, speaker in the Quantum AI monthly series by Bibliotheca Alexandrina, and Sir is also a speaker at the IBM Quantum Developer Conference held at Atlanta and New York in 2024 and 2025. So it is a very great pleasure to have you with us. And over to you, sir.
so thank you for having me. I realize it's already 7:30 p.m. in India, so I will make my presentation as enjoyable, easy to follow. But in about 45 minutes, I should have completed my presentation and the demo, and then I'm available for questions and answers, and we can go deep in technical stuff if you wish. So let's move on. So the topic is one some of you might already be familiar with this one because SQD was one of the topic of the IBM Quantum Summer School back in July, so it's a cutting edge algorithm known as sample-based quantum diagonalization. And there are a number of variants of this algorithm. It's really cutting edge, ongoing research, and very promising. And I will use a bunch of Jupyter notebooks that I've published on GitHub. It's a public repo, so feel free to have a look. And if you like my repo, then please start it. So this is I hope everyone can see. Let's move this to the right. The agenda. So first of all, I will put it in the context of the quantum-centric supercomputing. Then I will introduce a functional definition of SQD, illustrated with two big use cases that IBM Quantum have put forward. Great collaboration. And we will then focus on the second use case with Lockheed Martin and IBM. And it's interesting because it is of potential interest for sustainable and energy, and it's about optimizing rocket plum chemistry. It's also interesting for interstellar studies. And then, last but not least, I will demo the topic for which there is this use case with IBM and Lockheed Martin. And this is, I think, something amazing, is that a year after top researchers put forward this successful simulation, everyone can access the free plan of IBM Quantum and run the same experience, maybe not with the same accuracy, not with the same but nevertheless reproduce what has been achieved a year ago on publicly available quantum devices. And this is what I will demonstrate. And so let's move on. So let's see if I can, yes. So what is quantum-centric supercomputing? So it's a term which, to my knowledge, has been introduced by IBM Quantum, and they have made it applicable like an industry standard beyond IBM Quantum, thanks to their partnership with Pascal. Pascal is a manufacturer of quantum computers, a startup in France, but with offices in Canada, and Pascal use neutral atoms, whereas IBM, as I guess you know, use superconducting loops. So the idea is with quantum-centric supercomputing, we can achieve near-term quantum advantage in chemistry, material science, and other scientific applications in the near future. And so we don't have to wait a couple of years until the fault-tolerant universal quantum computers become mainstream. So this is really exciting. And by definition, a quantum-centric supercomputer is comprised of, guess what, quantum processing units, GPUs, graphical processing units, which are the key components of the high-performance computers, and CPUs as well. These are required to unlock the next generation of computing. I think it's important to realize that maybe the early wave at the beginning, I've been interested in quantum computing since I would say 2017. Initially, the focus was on quantum computing in isolation, I would say, and nowadays it's obvious for the industry, not just for IBM Quantum Pascal, but also Quantinuum, Microsoft, and others, that we will succeed, and I'm confident that this will come to fruition, provided that we integrate seamlessly high-performance computing, quantum computing, and artificial intelligence. So I think this is something, a key message in my presentation. This is the future is now, provided we integrate the three. Okay. What is, so this is a definition of sample-based diagonalization, which I like because it explains the what. It doesn't at this stage require deep knowledge of how it works. So what is it? So it's a chemistry simulation technique. That is what it was intended for at the beginning. But the good news is that there is hope that SQD could also be successfully applied beyond chemistry simulation. Okay, so SQD uses the quantum computer basically to extract a noisy, because the qubits nowadays are noisy, distribution of possible electronic configurations of a molecule in the form of bit strings. So as compared with other algorithms like variational quantum eigensolver or VQA in general, the quantum computer is merely used to do sampling, hence the name, sample-based, okay? And then it runs, so the SQD algorithm runs an iterative correction. We could rightly say that it is a kind of error mitigation, but an error mitigation that leverages the knowledge of the physical system, the molecule typically. So it's a smart error mitigation technique which can be used in combination with other error mitigation techniques and of course error correction. And so the iterative correction is done entirely on a classical computer to cluster these bit strings which come out of the sampling around the correct electron configuration. So that's the key difference with the variational quantum eigensolver and similar quantum classical algorithms that have been widely tested for the last couple of years, in that the iteration is entirely on a classical computer. So it is stated and hoped that for a large enough noisy quantum computer, which we have nowadays, even via the free plan, we can access quantum devices like IBM Brisbane. These are nicknames, and IBM Torino, which have 127 and 133 qubits. So we do have large enough noisy quantum computer to play with nowadays. And so if the error rates are low enough, so this is still yes, to be experimented with. So this technique, SQD, has the potential to perform more efficiently than classical approximation methods. So so there is no, to my knowledge, there is no theoretical proof that it does converge. There are other variants of SQD for which there is theoretical proof that it will converge. But there are, and this is what we are going to see in more details, there are very interesting experiments which have been made. On the left-hand side, there is a diagram. So LUCG, it's explained in the glossary of terms in my presentation. So it stands for local unitary cluster JASTRO. But basically, it's an ansatz, which is a good compromise between a purely between a ideal great physical based ansatz, but which cannot be run today on our noisy quantum processing units, and another flavor of quantum circuit which would be easy to run on a quantum circuit. So it's the choice of ansatz is actually very, very important. So part of the success of SQD, at least in the chemistry simulation arena, is this choice of LUCG circuits, LUCG ansatz. At the end of my presentation, I can give you more details. Okay. So the CCSD is a well-known classical technique in chemistry simulation, because quantum chemistry has been around long before quantum computing was so popular. Quantum chemistry is chemistry from first principles. Okay. And quantum chemistry can be achieved and has been achieved successfully for, I don't know, something like 40 years now, long before quantum computing was the topic, the main topic of the day, I would say. So in light green, we have the classical simulations using well-known classical techniques. Then the quantum part is basically to run the quantum hardware calculations and collect configurations into a dictionary. And this is done, of course, there are many measurements, but this is done only once. There is no, unlike VQE, there is no loop with a parameterized quantum circuit. And at the end, it's the very important post-processing with SQD. We will go into more details. Okay. I give credit to the source of this definition of SQD, and credit for the image. Okay. Now let's go down the rabbit hole, if you want, for the last part, which is called the self-consistent configuration recovery loop. Yeah, so this is very, so it might be relatively new for those of you who participate. I counted 75 participants, which is great for my presentation. So on the left-hand side, there are the 4 steps which are described. So number one is to post-process the full set of bit string samples using prior knowledge of particle number and the average orbital occupancy calculated on the most recent iteration. Yep. So this is a loop. So number one can actually follow number four. Okay. But so there is fortunately leveraging knowledge of the system to be modeled. We have a clue about the orbital occupancy, that is where the electrons are supposed to be. Okay, and in the iteration, the number one step, which actually in the iteration can follow number four, uses this prior knowledge, particle number, and the average orbital occupancy. Don't worry, you will see illustrations. You don't have to understand everything fully at this stage. And then the next step is to probabilistically create batches of subsamples from recovered bit strings. So the bit strings, which are, if you want, the output of the measurements, because we are dealing with noisy quantum processing units, there are errors. And this recovery loop can target the errors, which can be seen like very easily, because there are rules, symmetries which are imposed by nature, and we can detect discrepancies with expected, and then not only that, but we can fix them. So it's really error mitigation, fixing errors due to noise, thanks to the knowledge of what it should be in terms of symmetries. And then to project and diagonalize the molecular Hamiltonian over each sample subspace. So this is the secret of this, because what happens is why is it that we bother to project and diagonalize over each sample subspace? Is simply because the whole space it boils down to a much too big matrix to diagonalize, and it's beyond the capability of even the most powerful supercomputer in the world. I think it is Fugaku HPC from Riken in Japan, which is currently the biggest one. So the advantage of this self-consistent configuration recovery loop is that we break up this impossible to diagonalize, because it's too big matrix, into diagonalization of much smaller, manageable matrices, and so the Schrödinger equation, which boils down to this equation on the right, is solved for each batch, and then the algorithm, the SQD algorithm, finds the minimum current state energy, and also the average orbital occupancy. So in other words, the eigenvectors they give the orbital occupancy, whereas the eigenvalues give the energy levels. So this is the I think the important thing to remember is that the iteration is done classically, and the quantum processing unit or units just their role is to try and mimic the behavior of the molecule via a well-chosen ansatz. And of course, it matters to choose an ansatz which is as close as possible to the what we believe is the way nature works in molecules. So let's move on. Now I realize that some of you might be a bit disappointed to read this, because so much effort has been put in variational quantum eigensolver that back in 2022 when I illustrated the book Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code, it was obvious that it would be a huge challenge to make VQA work for molecules which are not too small for molecules of interest. And Matthias Treuer from Microsoft, who is a fellow at Microsoft, and I quote, he wrote that in order to reach the accuracy of 1 millihartree, which is required in quantum chemistry to provide any value, the ansatz should be close to the exact solution by 1 part in a million. So but for years we had nothing else but VQE to play with. But now the I would say the ugly truth comes out, because with the iron sulfur cluster, the simulation, an estimation with today's noisy quantum processing units, it would take 3 million years to for the variational quantum eigensolver to converge and simulate this sulfur cluster. So basically hopeless. I mean, there are many reasons, and I could during the questions and answer session I could give more details. But basically, it boils down to, first of all, in quantum chemistry, we're dealing with electrons, so it's fermionic Hamiltonian. But all the quantum processing units which have been manufactured so far, to my knowledge, they use a different statistics known as the bosonics. So there is a mapping between fermionic Hamiltonian and bosonic Hamiltonian, and there is a cost. There are several methods to do that, but that as a result, the quantum circuits end up having a huge number, hundreds of thousands of Paulis, and that means that the depth of the quantum circuits is beyond reasonable, several hundred thousands. Plus, there is the issue that the gradient descent is done classically, and we know that in many practical situations, the gradient descent fails because we have the issue of barren plateaus. Okay, and so for all these reasons, at least in the field of quantum chemistry, VQE is not the way we anticipate we would eventually get a quantum computational advantage. Now, quantum phase estimation, there is theoretical proof that we can get as close as we wish to the solution simply by adding qubits. And there are variants of quantum phase estimation which involve mid-circuit measurement, where you can reduce the number of qubits at the expense of having deeper quantum circuits. But still, a QPE on a fault-tolerant QPU, which we don't yet have, for this iron sulfur cluster, it would require 13 days run on a fault-tolerant QPU, which seems not realistic. Even on a fault-tolerant QPU, wow, 13 days non-stop. I guess it would be a huge challenge for the manufacturers, IBM Quantum in particular. So, but the good news is right now, with SQD, within a quantum-centric supercomputing framework, it can be done, this iron sulfur cluster simulation, in only about 2 hours. And I give the reference at the bottom. This was a great collaboration between IBM, Cleveland Clinic, and RIKEN. RIKEN provided access to their Fugaku high-performance computing system, HPC. There was a great collaboration. So it's not just a technical integration of HPC and quantum computing. IBM gave access to their at the time most powerful Heron quantum processing unit. But there is a key success factor is also putting together a multidisciplinary team involving not just experts in algorithms, quantum algorithm, but also mathematicians and of course people who know very well the topic of molecular simulations. So it's something to realize that it's a success, but it requires a great synergy, huge collaboration between a multidisciplinary team. Okay, and so right. So this is I think the cutting edge. This is very promising, but one must realize that yeah, that cannot be reproduced on a laptop because they used the supercomputer Fugaku to achieve this. Now the next use case I'm going to talk about is also very interesting. So it's a collaboration between Lockheed Martin and IBM to do chemistry simulations pertaining to combustion chemistry, but their studies is also relevant for interstellar studies when astronomers get a spectra from, for example, the latest James Webb Space Telescope, for example. The challenge is for them to interpret the spectra, and there are different scenarios, and it matters to be able to accurately model each scenario to help the astronomers make sense of the spectra they get, and also because in outer space the kind of chemical reactions that can happen is very different from what can happen on Earth. So it's not easy to reproduce experimentally what's going on in interspace. Okay, so now IBM and Lockheed Martin, they applied the SQD method within a quantum-centric supercomputing framework to simulate the dissociation of the ground state triplet and first excited single states of the methylene molecule, CH2. So you don't need to be an expert in quantum chemistry to understand what I'm going to explain. Is basically what's interesting about methylene is that there are two different states, the so-called singlet state and the triplet state, and the molecule oscillates between these two states. Okay. And it matters for the interstellar and combustion chemistry to have as accurate as possible estimation of the difference in energy between those two. Okay, and I will give more details, but what's interesting is that the authors claim that the benchmarks, so the SQD algorithm, it was the first time it was applied to an open shell system. An open shell system is a molecule where the outer layers, if you want, they are not completely occupied by electrons, which means there are several scenarios. So at the bottom, the triplet, there are the arrows, up arrows, that depict two electrons with a spin, the up, which is up, because the spin can be up or down, basically. And in a singlet state, the electrons have opposite spins, up and down, and they have the choice, you see, 3A1 or 1B1. So these molecules have different levels of energy. I will illustrate that in the following slide. I want to point out that these researchers used what was the most powerful quantum device available at the time, 52 qubits, and that was back in 2024, I believe. And for the last couple of months, at least I know, because I've been using the free plan for months now. We have had access to much more powerful quantum devices, and with the free plan, it's up to 10 minutes per month. So nowadays we have IBM Brisbane with 127 qubits, and IBM Torino with 133 qubits. And remember, when we had 1 qubit, at least in theory, it's like if we multiply potentially the power, the Hilbert space basically is multiplied by 2. So from 52 to 127, wow, it's at least in theory, because it's not so easy to make use of this potential increase in power, but it is huge. The difference, and also in terms of quality of qubits, the quality has improved quite a lot in about a year. So I think it's really important. Now the next slide explains in more detail what the researchers try to achieve. On the left-hand side, you see a beautiful diagram where horizontally it's the length of the bond between the carbon atom and one of the hydrogen atom, and it can fluctuate a bit, and vertically you have got the energy. Okay, and what is interesting, so there are different experiment. SQD is depicted in red. CCSD, which is a well-known classical algorithm, is depicted in green, and SCI, which is the most accurate but very almost impossible to use once the molecule starts to be too big, is in kind of yellow. And what you see is that if you follow the red one, well, it's fairly close to the SCI, which means it's a very good quality, because the SCI is the most accurate classical method. And you see something interesting where there is this rectangle. You see the two plots, one with 3 legs, another one with dots. They cross one another, and this is where the so-called first order phase transition occurs. That is to say, where the singlet and triplet states of the methylene molecule are exchanged. So and it matters for rocket chemistry to capture this as accurately as possible. Okay, so and of course I give the image credit. Huh? So and of course we will share the presentation will be made available to all participants, so you will be able to check and have first access to the original papers. Okay, I'm just curious, is there the date? Yeah, you see, the papers were published in this year. However, the study was made the previous year. It takes so long to get a paper published that by the time it is published, there are people like you and me who can reproduce the experiments. We are cutting edge with much more powerful devices. I think we live in an incredible time, really. Okay, so let's move on. It's demo time. So I will explain the demo, and then I will run the demo live. It's the outputs of the results of my demos are all shared in a repo, publicly accessible. Yeah, you can and everything is published with an MIT license, so you can copy paste and download the Python code and Jupyter. It's well documented. So everything I will show to you, I will encourage you to download my work and see for yourself. Okay, so the first demo of SQD is what we are trying to achieve is to find an approximation to the so-called carbene single state CH2 molecule in the 6-31G basis set. So 6-31G is the acronym of one of the basis sets. There is a definition of what a basis set in the glossary, but basically in classical quantum chemistry for years now, there is a vast catalog basis set. It's a set of basis functions. So people have spent years of research. Some PhD students have devoted their the entire time of their PhD work to try and improving the performance of a basis set or finding a new one. So there is, and 631 is one which is runnable on with reasonable amounts of resources for small molecules. It's much more accurate than the Store 3G basis set, which, by the way, has been demonstrated in my book, Quantum Chemistry and Computing for the Curious, where we use actually the VQE, but we use VQE. There is a demonstration of successful use of VQE for H2 and lithium hydrate, so very small molecules. But 631 is more accurate. Okay, so yeah, it gives more details. The first excited state is called a single state, where the two electrons in the carbon atom are paired and one orbital is empty. Yeah, so they are paired. One with a spin down, one with spin up, and they are and one orbital is empty, and there is a choice. There are two actually different configurations, singlet state. Okay, so I used actually I got help from ChatGPT to help me provide a good PySCF. PySCF is a well-known classical package in quantum chemistry. Pi for Python, SCF as a starting point. Okay, so I give the Jupyter Notebook. We will jump into that fairly soon. Okay, so I will explain that in due time. This is the result. So earlier on, I talked about the energy. So this illustrates the iteration of SQD. We start with fairly not so good approximation, because yeah, this is the time to mention that. What's good about SQD is that usually it involves, for the molecules of interest, it involves more than 22 qubits, which is at least for people who can use a laptop with, I would say, only 32 gigabytes of memory. 22 qubits is the practical limit of what you can simulate with AR simulator. Okay. So what happens is that the recovery procedure is so efficient that you can make it work with a uniform distribution. So instead of starting with a noisy set of bit strings, we can make it work with a uniform distribution. Hold on, but that only works up to a certain size of molecules, because yeah. So that's why I will be able to demo running these simulations on a laptop, running Ubuntu under Windows. Yeah, because we can start with a uniform distribution. Okay, but of course, if we have already run on a with the LUCG quantum circuit, then we get better quality bit strings, and then we can run the SQD. But look, it seems to work really well, at least for the singlet, because in less than 4 iterations, this is the milli-Hartree, the chemical accuracy. So it shows that after 2 iterations, which have actually reached the chemical accuracy, starting from a really poor approximation. So it works really well. On the right-hand side, you see the orbital index. So which means there that the first 4 orbitals are fully occupied. Which, if I go up, yeah, which is consistent with this. Okay. Yep, they are yeah, it's fully occupied, as opposed to there where we will see the difference. So for the triplet, which is opposite at the bottom, so okay, the carbon atom's outer shell contains 2 unpaired electrons. So they are you see, they are in different orbitals, and they have parallel spins. So that leads to a total spin of 1. Yeah, because the spin of the electron is 1/2. So 1/2 plus 1/2 is 1. Actually, but the thing is with PyCF, the classical chemistry package, on which quantum, I mean, for VQE, it's always start with the PyCF base first approximation, and then it is refined. With PyCF, there is what they mean by spin is actually the number of unpaired electrons. So you would see in my simulation, I use a spin of 2 words. Actually, strictly speaking, it's a spin of 1. But when we see the results, you see the difference. So it is more work to reach the mini-Hartree, 10 to the -3 1,000ths accuracy. And we see in terms of orbital that there are 2 orbitals which are half empty. So so this is a success. So it means that this simulation has been successful. Okay, so now let's move on to the so I hope it will work fine. So just bear with me. I will not stop sharing, but I will try escaping from the can I escape from this? Hold on. Yes, I managed to do it. Great. So now I'm going to move to the Jupyter lab. Okay, it's okay, so I guess you are all familiar with Jupyter notebooks. So I will go to the singlet, which is already there. Okay, so yeah, if you want to reproduce this, it's very well documented. But of course, I welcome feedback. And so let's, I guess you can all see my screen, hopefully, yeah. So I'll just restart everything. And then I will run all cells, but actually there is only one line which is executed, which is this one. So Gradio is a Python package which makes it easy to write a user interface with only you will see. So I click there. Okay, hopefully, yes. So this is my user interface. I hope you can see it. I had fun. I had no previous experience with Gradio. I mean, I just did it in a couple of days. It's really so the way it is designed. First of all, I can load the configuration from a JSON file. So this is the name of JSON file. It was actually found to be in the same directory as Jupyter Notebook, so it was already there. So I load this configuration. Have a look. Yeah, this has changed. I guess it has changed. So I can say whether I can run on a QPU or not, and there it lists the list of IBM devices I can access, and it is not hard coded in my code. It's really say next week or in a month we have access. I have access to new IBM devices. They will show up in this drop-down list box. None stands for list busy. Okay. But I won't do that. I won't do that. So this is the basis set I mentioned, the set of functions which are used to. So this is classical chemistry. Okay, there is the I can load a bit.array file. I will show you, for example, for let me show you for nitrogen. And by the way, this is the one which was the topic of the IBM Quantum Summer School. So I've got a bit.array file which is ready. Okay, but for the singlet. I don't have a bitI file, so I don't have one. At the end of the simulation, I can save the bitI file, okay? So which is convenient because say I've run this on a quantum processing unit. It's good. I can save the bitI file and then I can run other simulations of the recovery, basically, but with the same input, okay? Compute exact energy, which is handy when there is not enough memory to compute the exact energy. Plot get map, it's interesting when there is a when running on a QPU. This is quantum chemistry, basically. It's by CF. It's explained. There are many symmetries possible, but this is also critical because, as explained, the recovery procedure, it's basically mitigation technique, which leverages the knowledge of the symmetry and the many different symmetries. So it's critical, of course, because otherwise the whole algorithm will not work. The spin, in the case of the singlet, it's 0. Okay. So limit the number of configuration recovery iterations, so between 10 and 20. So I say run simulation, yes, because I could just take this configuration and save it, but I will run simulation, no QPU. Okay, so I will press this, and now it starts running. Okay, you can see maybe the clock over there. So let's go back to this, and you can see it has started. I hope it's big enough. I will make it slightly bigger. So this is we are in the Jupyter notebook. This is kind of a log which explains all the options, and then yes, this is, it's not cheating. I mean, it's perfectly valid, but yeah, it doesn't run on a real quantum processing unit, and it doesn't run air simulator either. And the reason is quite simple. The number of qubits, 26. So we are way beyond. Maybe this would still be doable on a workstation, but no, with only 32 gigabytes memory that I have to play with, it's definitely not possible. So what happens is I use a function which is out of the box from the SQD add-on, which generates 10,000 samples from the uniform distribution. So it's really bad as compared to what we would expect from by running on a quantum processing unit. But the so it's not stuck. It's simply it's number crunching. I mean, it does require some effort on this. I've got a more powerful laptop, but it takes a while to run. But in the interest of time, I want to show you another simulation. So we will visit this notebook every so often. I want to show you what happens with an N2 nitrogen. So this is the so this is, let me show you. Yeah. So let me go to N2. Okay. And I will show you the way it looks. So I hope you can see. So yeah, the difference there with this simulation, I was lucky to have a saved bit strings, a set of bit strings which are already saved. So I just mentioned that in my simulation, and so the corresponding run for N2, we are talking about N2 was very smooth, as you can see. And so we reached the chemical accuracy in just 9 iterations from a not so good starting point, basically. Yes, actually, this is a high quality input because it is really the output of a quantum circuit. Okay, But what I wanted to show you is what happens when we use. I did another demo. Sorry, I've got to move this out of the way. And to test, where I start with, you see, oops, SQD config and run and to test. That's interesting. Maybe because I changed it recently, but basically the run using a uniform distribution, you can see that it eventually managed to reach chemical accuracy, but it's not as smooth as the one where I used the bit string from an actual run on a control processing unit. So the bottom line is that for small enough molecules, yes, we can successfully run SQD, but beyond a certain size, yeah, I mean, it won't work anymore. Okay, so that's what I wanted to share with you. So if we go back to the simulation, you see it has started. It's the first iteration. So there are 5 samples, 0, 1, 2, 3, 4. And yeah, it starts working on this, but it takes ages, as you can see, because there are 9 iterations we saw earlier on. So in the interest of time, I will abort this, okay, if you don't mind. So let me go, make sure I go to the singlet, and I will show you the okay. I will show you the triplet. So if we see the okay, so basically it's much more work. Huh? So again, yeah, again it was starting from 10,000 samples from the uniform distribution, and it took you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It took 10 iterations to converge. So the exact energy, well, which is computed classically, is this, and the SQD energy is this, and we are well within the millihartree in terms of accuracy. It took 159 seconds, and it is on fairly powerful laptop I've got with 32 gigabytes of memory. So if I'm correct, it's I think if it was 2 minutes, it would be 120 seconds, right? If it was 3 minutes, it would be 180. So it's in between 2 and 3 minutes. It took a bit in between 2 and 3 minutes to run, but yeah. So this is what I wanted to share with you, the demo. Now I would like to share with you the what's available on GitHub. So I guess you can see it's there. This is the one, and so the README file is pretty well documented. At least I hope so. There is all the MIT license, so you're free to reuse, so long as you name the author, and also I give credit to the original work, which is actually just click on there, which is published. It's part of the Qiskit add-on SQD documentation. So yeah, you will recognize this. Of course, I didn't invent it, but this is focused on just N2, and yeah, and they didn't reach the chemical accuracy. At least I think it's because they were just too shy in terms of number of iterations. But this is the original work. Okay, so I'm started from this great work. I made it more generic to work with. So let's go back to the where is, oh yeah, I just have to go back. So I run this SQD with a variety of molecules, C2H6, CH4, methane, CO2, and yep, and also nitrogen, the molecule. This was also discussed, and this was the topic of one of the labs of the quantum summer school. So I guess some of the participants would remember. Maybe they struggled a bit. I'm sure they did struggle. It was not so easy, actually. It was quite challenging. And yeah, it is reproduced there. So I think this is what I wanted to share with you. Now I'm open to questions. Don't be shy. Every can be related to SQD, but I've also other topics. I mean, QPP is the quantum permutation pad. It's sort of very nice. This is for not for quantum chemistry. It's for cryptography. Okay. There is also the while I can show you this is the a fork of the quantum chemistry and computing for the curious. The repository by Pack Publishing, and I'm contributor of this repository, but because there is work in progress with Qiskit Nature, I've published a interim, I would say, a temporary fix. Yes, that's the word, temporary fix, to make so these notebooks basically reproduce all the experiments which are documented in my book. So this is the cut down version, which is just the code. But those people who buy the book by Dr. Kipperle and Sharkey and myself, they can get a more complete version of notebooks with images, text, with LaTeX formulas, and of course the code. And so those of you who are really excited by VQE, you can also have fun reproducing the making VQE work with small molecules with H2 and lithium hydrate. Okay, so it does work. I mean, VQE works, but for small molecules, it works. Yes. But if you look here, for example, I wanted to show you lithium hydrate. Okay, if you see the plot, so this is what we get with the SQD. In in less than one iteration, it finds the energy and orbital occupancy. So it shows the SQD is much more efficient than was VQE for this molecule LH, because I can tell you that the yeah, it is struggling. I mean, LH lithium hydrate. So it is tough for VQE to make it work, but it does work. I mean, but that was the state of the art, I would say, 3 years ago. But nowadays, SQD is definitely outperforms VQE. Okay, so this is what I wanted to show you. There is also in my there is also I've also published Jupyter notebooks from another great author. Yeah. So those of you who want to learn about Qiskit, and so this is a great book by Robert Loredo, and I've updated the Jupyter notebooks, which enable you to run all the examples in this great book with the most recent versions of Qiskit and also the new IBM quantum platform. So that's it. I'm open to questions. You might be a bit tired given the time, but I'm available for questions if you wish. I will stop sharing for now. Okay. Okay.
So thank you so much for your kindness for spending so much of time, and it was very, very interesting. The GitHub codes, and you have shared your research work, which you would have done over a long period of time. And we are very, very happy to have such a renowned researcher in quantum chemistry with us to share your expertise to all the participants. My request to the participants, if you have any doubt, you can have the chat box. You can post your questions in the chat box. And also, if you can unmute and ask the doubts, that is also welcome.
So thank you. It's gratifying to have that many 61 participants.
Yes, yes.
It's really great. I realize it's late in the late afternoon and or
Yeah,
even
it is a
evening, and
night here, sir. Night
yes,
time here.
and I realize that you must have had
So there
several
is a
hours
feedback
of
here from the
yeah.
participant. Thank you so much. Very nice and informative session. And there is one question, sir, which is in the chat box, but I don't know whether it is related to your domain. I will read it out, or can
Yes,
you read
please.
it, sir? Oh, okay, many.
Um,
It is there in the.
so I see. Thank you, Alain.
Yes.
Sir, we need titles for filling feedback. I'm not sure exactly. Um, yeah, help
Kiran
me out,
Patel.
please. Oh, yeah, I see questions now. Number one, I think, okay, is it many a times people connect machine learning with quantum computing? I'm wondering how quantum with a condition to have a separate dedicated hardware be used with machine learning, which normally runs on traditional hardware. Okay, so quantum machine learning, very interesting topic. Back in 2019, I had the opportunity to interview Peter Vitek, who at the time was one of the pioneers in quantum machine learning. Unfortunately, he died in an avalanche in the Himalayas. At the time, back in 2019, there was much hope that quantum machine learning would deliver value beyond what can be done with classical machine learning, even with noisy quantum processing units. Unfortunately, it turns out that the best experts in the world, they found out that first of all, there was no evidence, theoretical evidence of a generic advantage with quantum machine learning as compared to classical machine learning. But that doesn't mean that for certain topics we would not achieve quantum advantage with quantum machine learning. I mean, my background, I've spent so many years especially in consulting, but with data management, master data management, data governance. I know it matters. The structure of data matters a lot. I think in the quantum computing arena, people tend to focus too much on the algorithm, and they forget about the importance of the structure or lack of structure of data. So my intuition is that just like when you think about it, the Shor's algorithm is successful because it does exploit properties of prime numbers. Okay, it comes from group theory. And I think the early attempts with quantum machine learning were worth doing it, but they didn't provide conclusive evidence of any advantage because, more work is needed. I think it's an open research topic. There are issues I mentioned earlier on, which basically quantum machine learning with algorithm which involved gradient descent face huge challenges because it's not fair. I would say it's something I mentioned, I think, in the introduction of my book. Basically, it has been shown by experts that the gradient descent is an NP hard problem. Okay, so but in the VQE and variational algorithms, it's not fair because the classical computer has got to do the heavy lifting with the gradient descent, and the quantum computer does the easy work, I would say, which is enabling the measurement of expectation values, right? But I've not seen, to my knowledge, there might be, but it's not mainstream a quantum gradient descent, because then that would be maybe a game changer. So for all these reasons, unfortunately, quantum machine learning, the way it was defined initially, I would say it's still an open research topic. My intuition is that if people would care about the structure of data, for example, in finance, you have patterns, you have cycles and things. Intuitively, you would expect that, that could be a good fit for quantum machine learning. So that's my my view. But I mean, for those of you who are really invested in quantum machine learning, don't despair. It simply means, on the other hand, it's an opportunity to shine by being maybe the first to show some advantage. But I would advise those to focus on a interesting topic of much interest for industry or research or astronomy or whatever. And then, tailor, try and come up with a variant of quantum machine learning that is really fit for purpose. Okay, that's it for me for this question. Number 2, quantum will break traditional security algorithms such as how real this threat is in day-to-day real-time scenarios. The threat is real. I mean, I'm a member of Quantum Security and Defense Work Group, which is and anyone can join. It's public information we share. So there are experts who talk about post-quantum cryptography and also quantum key distribution and I can tell you one thing. Yes, the threat is real for one very simple reason: is that it's the threat which comes from the future. Okay, so it's not back to the future, but it's basically the problem is the following. Even if it takes another 10 or even 15 years before the Shor algorithm can be used to crack the RSA algorithm, which is from reverse Gemea-Adelman, which is the basis of the asymmetric, public key, the initial exchange between two parties before they use symmetric encryption. The issue is the following: is that data is being stored nowadays by big agencies, okay, with 3 letters usually, but also maybe by bad organizations. So they store, they intercept communication, they store it. They cannot decrypt it now. However, in 10 years, 15 years, once the powerful enough quantum computers are available, hopefully, then they can crack the code that were used 10, 15 years ago. So it means that some people hold the view it's already almost too late. It depends also on the data. Some data, medical data, other things. The data protection, there is regulation in a number of states, number of countries. This data must be protected for the lifetime of a person, for example, medical health data. And unfortunately, this has been encrypted with what was available, and it's almost too late to start using post-quantum cryptography now or quantum because it only applies from now on, and so the data which has been copied, store now, decrypt later. That's the threat. So yes, the threat is real. It is real. And another thing I would like to add. Okay, imagine some team somewhere around the world managed to be successful and they have a very efficient quantum computer and okay, guess what? It's very likely that the authorities would say, congratulations, now your work is classified for strategic reasons, defense, right? You're not allowed to talk about your success with your wife or husband. This is classified. Now you work for us. So maybe some team could be maybe this breakthrough won't be made public. And then maybe some team could exploit this to their advantage and crack the code and so yes, the threat is definitely real, and I think the best measures is to combine post-quantum cryptography, which algorithms which are supposed to resist quantum computer attacks from quantum computers, plus physics-based encryption technique, typically quantum key distribution or physics-based encryption techniques. But the threat is definitely real. Yeah. Okay. Have I got the time? Number 3, as quantum requires very costly hardware, military industry can be one of the many application domains. Any other applications domains, sir? Well, yes, there is obviously very costly hardware, centralized, and it's particularly obvious with the quantum-centric supercomputing model. However, there are also researchers and entities, they work on different flavors of quantum bits that work at room temperature. So, for example, nitrogen vacancy centers in diamond, okay, and these centers that works at room temperature. And so, who knows? No one can claim that only big data sensors are only available to a select few, or maybe via the cloud. You know, I mean, who knows? Maybe some technology will be successful, and we will have hardware that fits in a shoebox. That is possible. Application domains, well, typically, okay, quantum chemistry, because the challenge is we need accuracy, good accuracy. Otherwise, there is no value. In finance, maybe different. If you know the trend, it's going up or down, okay, maybe good enough. But in chemistry, accuracy is paramount. So, and we are stuck because the problem with quantum chemistry, again, which existed long before quantum computing was a popular topic, the issue is the algorithms, the methods we have nowadays, they work well. But unfortunately, the scaling is exponential with the number of electrons, basically. So after a certain number of electrons, we cannot model efficiently, and so there are folks who spend years and years of research finding the good compromise, and one of them, of course, is Taha Selim, who is a co-founder of Molket, and he got his PhD from university in Netherlands, Radboud University, last year. It's the art of compromise, getting good accuracy at an affordable price. And so quantum computing is really a good application for that. But more beyond quantum chemistry, so material science, but also optimization everywhere, because today we have heuristic algorithms which work reasonably well, but we don't get the best solutions. And there's many applications in the airline industry, for example, for optimizing the flights of many, optimizing the routes, optimizing the loading of cargo in a plane or elsewhere. There are a number of applications, and maybe some of the best applications are not yet found, but they will be found eventually. Any other question? I'm open to question. There is no. If I cannot answer, I won't answer. But
Also, there is a question: can we apply quantum chemistry to discover new molecules?
Well, that would, yeah, hopefully yes. Because that would be really, and not only that, but the big hope is that to be able to simulate molecules much faster than can be done today. Nowadays, it's the same also for medicine, for because we cannot simulate classically. We have got to run experiments on real molecules. So it takes ages. But something even more exciting is that we can combine HPC, quantum computing, and AI and robotic to so it's not just simulating, but it's also actually manufacturing those molecules. And I made some presentations on this topic, I think this year and last year too. So we can have the whole workflow, including up to the robot, which will mix and stir and produce the molecule. And then you can think about quantum sensors, and so I have a feedback loop and say, oh, no, the properties are not exactly what was modeled, so something must be wrong. So you could think of an iterative loop whereby the but it's a synergy. So the HPC would pave the way, would try and focus the work on of the quantum processing unit to what is difficult to achieve classically. And then AI with typically surrogate modeling, we try to make the because it's costly to run those quantum circuits. So with a few data points, with AI, with surrogate modeling, you can extend, if you want, the number of data points, and then you put that as input to some kind of a robot, which creates the mixture. You measure the properties, and then you loop back, and that kind of loop would be achieved much faster than today. So there is definitely huge value expected there. But it's not just quantum computing in isolation. It's part of a process, and AI is really important there as well. Okay.
Thank you so much, sir, for your elaborate discussion and answering of the queries by the participants. And we are very happy that you take time to interact with the participants from India. And I am personally very happy to collaborate with you for this online discussion, and hoping to collaborate with you in the future also, sir. And once again, from the management of KCT College of Technology, from the organizing team of this ATAL sponsored FDP on quantum computing. And on behalf of all the participants, I extend our sincere gratitude and heartfelt thanks to you, sir.
Thank you. It's my pleasure. I mean, it's my pleasure. It's really gratifying to have so many students at this late hour, and I mean, you can invite me in the future. I mean, and we can exchange more.
If you do
That's
happen to
great.
visit India, please do visit our institutions.
Sure.
And yeah, we can plan that also, sir.
Thank you to you, and thank you to the
Thank you,
organizer.
sir.
Thank you to all participants.
Thank you. This is
Goodbye.
Dr. Chipa signing off. And thanks to Dr. Elaine once again. And tomorrow we have the fourth day of the session. All of you are requested to join back again tomorrow evening at 6 p.m. We'll have a hands-on session. Thank you. Bye-bye.